Well, it gives me great pleasure to introduce Nicolas Gisin, who something of a legend in foundations community. It's really a pleasure to have him here today. But he was inspired by this conference, I think, to put a paper on the archive last week. I don't myself recommend it, but some may find it interesting. Anyway, so Nicolas, you're going to talk on many worlds in classical mechanics. Thank you. The stage is yours.
Okay, so, well, thank you, Simon. Indeed, the paper I put on the archive is a translation of something I wrote 15 years ago, but it was in French, so completely unknown. And actually, my talk of today has nothing to do with this little one page that I published last week. Okay, so the title, Many Worlds in Classical Mechanics, and the main goal or motivation is really to bring classical closer to quantum. Usually people do exactly the opposite. Now it's a century that we are trying to bring quantum closer to classical. But by bringing classical closer to quantum, the hope is to see which features are truly quantum and which ones are actually already present in classical physics. So let's see that. And just to give you the main message immediately from the start, the first of these messages is whether Newtonian classical mechanics is deterministic or not is not a scientific question. It really depends on the physical significance one associates with mathematical real numbers. I'll develop that, of course. The second one, the mathematical language we use when speaking physics has a huge influence on the worldview that physics presents us. We all know, I'm sure that here everyone speaks more than one language, and we all know that depending on which language you speak, there are things, ideas, concepts that are easier to express in one language than in the other one. And mathematics, we maybe believe that there is one mathematics, but actually there are many mathematical languages. We are usually trained and have been selected for swallowing all the Platonistic mathematics, so that's the usual language we are using, but it's not the only one. And I'm going to present you another language, which is called Intuitionistic mathematics, which automatically, just by changing the language, having the same prediction, so the prediction don't change, but this different language naturally tend you to interpret also classical mechanics quite differently. So the third message, we face a choice. Either our stories present events as the consequence of long past initial conditions, that's the traditional view, or else we understand the present as a result of indeterminate reality, and the future is open. And the last one, much of quantum, which is essentially the main conclusion, is actually also classical if one considers classical as indeterministic. And you can already guess from that many worlds is not specifically quantum. Okay, let's start with deterministic chaos. So because this is not my computer, this thing doesn't move, but you have enough imagination to understand that this is Brownian motion. And usually one always says Brownian motion is a typical example of deterministic chaos. And so the question is that really so? Or does it depend on this mathematical language that we usually use for classical mechanics? And so Yuval Dolev, who is a philosopher here, well, in Tel Aviv and in Jerusalem, he lives in Jerusalem, but I think he teaches here, he wrote that tense, passage, and passage are not, never were, and probably cannot be part of physics and its language. And so one of the claims is to say if you change the language, the mathematical language, it changes this statement. But let's take a much more simple chaotic system, the well-known Baker's math essentially, but in one dimension. So the state space is just a number between 0 and 1. Let's say it's the probability of rain. So today it is close to 0. And then during one time step, you stretch that and you fold it back, and this is the equation. But let's look at the equation written in binary form. So it starts with 0 dot, and then you have a string of bits. And this transformation just maps the second bit to the first position, while the first bit drops out. The third one becomes the second one, and so on. Consequently, whether x lies on the left, so it is sunny, or on the right half, rainy, after n time steps depends on the nth bit of the initial condition. Just moves one by one. And then the natural question for a physicist is the following. Is the billionth bit physically real? So of course the question is not whether this billionth bit can be measured. For sure it cannot be measured, but whether it corresponds to something physical. So let's look at typical real numbers, because if I go back here, if this billionth, and not only the billionth, but all the bits are considered as being really real, that's a typical real number, mathematical real number from Platonistic mathematics. So let's look at typical real numbers. Well, the typical real numbers, those that you have already met, they have a name, and they are defined by a finite algorithm, like these ones. And the bits of a typical real number, they have no structure, hence they have no name. And the bits are random. They are as random as quantum measurement outcomes. So a good way to think of a typical real number is just what comes out of this quantum random number generator, photon beam splitter to detect us. Actually, it goes further than that. Because we have only countably many names and algorithms, typical real numbers, those that don't have a name, don't have a structure, so don't come out of an algorithm, they contain infinite amount of information. And Emil Borel, well-known mathematician, noticed and emphasized that one single real number can code for the answers to all questions one can formulate in any human language. So that's just a way of really emphasizing that you have really infinite information. And Gregory Chatin, who is a specialist in complexity, wrote that this is not only one way of thinking of a typical real number, but it's the only good way. So when we say let x0 be the initial condition, what we actually are saying is let x0 denote an infinite amount of information. Now, if you make an assumption, which you buy or you don't buy, but I would like to mention that, I think it's a very natural assumption, namely the assumption that in a finite volume of space, you cannot have but a finite amount of information. So in this little cube, for instance, if you have a beard ball in it, or any marble, then the position of that classical particle cannot be faithfully described by a real number, because a real number would mean that there is an infinite information here. So let me now show you how I see a typical real number. So a typical real number, let's say it starts with a 0, and then you have, okay, in this case, digits. And they come one after the other, and you easily see that, according to this intuition I have of real numbers, is going to continue. And if we have enough time, the screen will be full. And when it continues, will cross the Earth, it will go on, it will cross the galaxy and go out and go on forever, infinite. Okay, so that's the view that I have of a real number. But a classical mathematician will tell me, no, that's not correct. For the kind of mathematics that we are used to, a real number is the following. Just pay attention, look at the screen. Now, infinite information in 0 time. That's beautiful. Infinite information in 0 time. Beautiful, but not physical. So here, instead of indeterministic events, like these digits or events in physics, happening as time passes, according at least to this classical mathematical description, all the indeterminism is coded in the initial condition. So instead of God playing dice as time passes, God played all the dice at the Big Bang and coded all the outcomes in the initial condition. So I hope I conveyed the message that the mathematical language forces us to speak of deterministic chaos. It's not physics that tells us that chaos is deterministic, it's the math. And here let's now turn to intuitionistic mathematics, which is this other sort of language that I mentioned already. So according to these, let's say, mathematical or classical mathematics, real numbers are not physically real. Or the catchy sentence is, real numbers are not really real. Maybe you just remember that one. And so Karl Popper, who is another philosopher in Jerusalem, who is the person who introduced me to intuitionistic mathematics, wrote, "There is no infinite helicopter allowing us to survey the whole terrain, all the future, see all the folks that are there, or to tell us how things will look at the end of time." And how do the real physicists, the experimentalists, or the very applied one, how do they do that? So for instance, Tim Palmer, who is a specialist in climate physics, certainly a very timely topic, how do they do that, these climate physicists? They have huge computers, but finite. And then they put into these huge computers the initial condition. Well, no, they put as much as they can. I mean, at some point, the computer is full, even if it has very large memory. And then they start running the simulation. And because this is a chaotic system, very quickly, they need additional digits. We don't have them. How do? They just add stochastic reminders. Exactly the way I was presenting my intuition of real numbers. When it becomes necessary, these additional small digits, they don't have structure, so you can just put random bits in it. That's good enough. And that's the way actually we are simulating the climate, one of the important topic in physics today. So also you start to understand that in this new language, statements about the future can be neither true nor false, but indeterminate. They are presently indeterminate. Hence, the law of the excluded middle does not hold. That's the main probably change between classical mathematics and intuitionistic mathematics. Okay, so these are already said. So this intuitionistic standpoint. So again, Karl Popper, we humans have finite memory, finite attention span, finite lives. So we can fully grasp only finitely many finite-sized pieces of a compound thing. There is no infinite helicopter. And another specialist of constructive mathematics, Bishop, he wrote, "The classicist," so from classical mathematics, "wishes to describe God's mathematics. The constructivist to describe the mathematics of finite beings, man's mathematics for short. Constructive mathematics does not postulate a pre-existing universe with objects lying around waiting to be collected and grouped into sets like shells on a beach." And Brouwer, who is really the father of intuitionistic mathematics, "Nature simply has not yet fully determined all objects. This can be compared to the uncertainty principle used in quantum mechanics." The last part is mine, it's not Brouwer's. So that's the essence of intuitionism. But don't get worried, with this kind of mathematics, you can compute everything. After all, there's probably nothing more complicated to compute than the climate in a century and several centuries. So everything you can do on a computer, which is clearly finite, you can also do here. Okay. So in about a century ago, there was many big meetings. We all know about Einstein and Bohr and these kind of people. But there was also David Hilbert, whom I take here as the figure of classical mathematics, and Brouwer, who is here the representative of intuitionistic mathematics. So on the classical mathematics side, every real number is an individual completed entity. Boom, everything at once. Infinite information in zero time. So all digits are given at once. And the continuum, the numbers between 0 and 1, for instance, is a collection of individual points. And so real numbers exist outside of time in some ideal Platonistic world. Now, if you use a language which is from outside of time, no surprise that it will be difficult to express ideas and concepts that involve time and involve the passage of time. On the other side, intuitionistic mathematics. So here, and I will develop that a bit more, real numbers are processes that develop in time. So time appears from the very beginning. Digits are not all given at once. The continuum is and I explained that also, a viscous collection of processes. So here time is essential to intuitionism. At any instance, only finite information exists. So let me tell you a bit more about intuitionism. Of course, no way to that everyone gets everything about intuitionistic mathematics, but maybe some kind of understanding. So Brouwer, he introduced this concept of a choice sequence, alpha of n. So n will be the time, discretized time. So we have, that's the nth instance of time. And this sequence, you can really think this is really the idea of this evolving process. And according to Brouwer, these choices were made by an idealist mathematician. So that's really not very physical, but his idea was, mathematicians solve problems, and so things that were unknown become known. But that's not the way I want to continue. So I'm going to assume that nature has the power to produce true randomness, to produce new information. And if you want really to follow this idea of intuitionistic mathematics, things evolve in time, I think there is not much choice. So I'm going to introduce this concept of a natural random process that outputs random bits. Okay, bits for simplicity. And we're going to use these bits to produce these choice sequences. So at each time step, a natural random process outputs some random numbers, and alpha n is computed via a computable function from the previous one, from the time, and from the existing information. So only the past and finite number of random bits. And it converges. There is some convergence assumption here. Okay, let me give you some examples. The first example is the most obvious one, where you just choose the last random bit as being just the next bits. Okay, before it was digits, but you understand. So you have just put the next one at the end of this series, but it remains finite. At finite time, it is finite. Second one, computable number. Of course, computable numbers still exist. And there, the definition says you'd only need a finite, a limited, it goes only up to some finite k here of information, which just tells you actually which of these random numbers, computable numbers, this is going to produce, this choice sequence going to produce. And so this is typical pseudo-random series where the seed is given by this initial kind of key, we would say, or seed. And the typical computable number is pi. Here is, for instance, one algorithm that allows you to compute pi, but I've chosen to show you this one because this one has some remarkable property. Namely, the bits may certainly look random, but they're actually all hidden in the algorithm. And in this algorithm, it allows one to compute the nth hexadecimal of pi, hence also the nth bit of pi, without computing the previous bits. So you can decide, I want to know bit number 1,000,000 of pi without the necessity of computing and waiting for all the previous ones. One can jump ahead. And the fact that one can jump ahead clearly indicates that the bits of pi don't come one after the other. They are all already there. So here's another example. Let me go fast. So here, instead of just taking the last one, you take the majority of the k last ones. Okay. And some that I like to call mortal numbers, so the terminology are mine. So this is an interesting example. It's actually really due to Brouwer, although I changed the terminology. So here you have a number defined like that, which, as you see, is fluctuating around 1/2. So it's 1/2 plus or minus, depending on the value of the last random bit. And it's getting closer and closer to 1/2. So it just, it fluctuates around 1/2. And that goes on until, by chance, the last half random bits all happen to have the same value. And when it stops, when the number or the process dies, it doesn't evolve any longer. But of course, in advance, there is no way to know whether it's going to die just above 1/2 or just below 1/2 or continue forever. Because indeed, with this rule here, or this stopping rule, the probability of termination decreases exponentially, so there's an a priori probability that a sequence goes on forever. So the statement, a proposition like alpha is smaller than 1/2 is never true, because it could stop above 1/2, never false, but indeterminate, at least as long as the number did not die. And here another example, that's the last one, of an autonomous number, so a number where the law does not involve the time explicitly. Okay, never mind really, you can look at that. But interestingly, this is extremely, so for those who know GRW, that was already mentioned, or stochastic Schrödinger equation, stochastic Schrödinger equation is essentially using these kind of processes, and here you have some examples of these GRW or quantum state diffusion models that start with a superposition, in this case of odd photon numbers, and it eventually settles at one photon number, so it goes to one of them. So here already you see that this kind of evolution that is known from quantum mechanics, that is from GRW, you also find in classical, in intuitionistic mathematics. You also have logic with intuitionistic mathematics. Okay, so I already said this is indeterministic, and I think I like to put these, so this is a mathematical proposition, of course, and I can now put it in parallel with the physical proposition. It will rain in exactly 1 year from now at Piccadilly Circus. So if you believe in indeterminism, this proposition has no value. It is neither true nor false. For sure, it is not known, but I'm not talking now about epistemology. But fundamentally, in an indeterministic world, this kind of proposition is indeterminate, like this one here. So the law of the excluded middle is not valid. Consequently, you have no non-constructive existence proof. That is surprising. We are used to non-constructive existence proofs, but it makes a lot of sense not to have them in an indeterministic world, in a world in which the future is open. So the elements of the continuum, according to intuitionistic mathematics, are these sequences, choice sequences, and some never terminate. So they continue forever. And because of that, you cannot cut the continuum in two. You could not have a step functions that is, let's say, 0 up to 1/2 and 1 above 1/2. Because this mortal number, you wouldn't know whether you have to put them on the left or on the right. Are they smaller or larger than 1/2? They don't have yet a value. And consequently, and this is the most, well, one of the important theorems called Brouwer's theorem in intuitionistic mathematics, which is clearly not correct in classical mathematics, that states that all total functions, so all functions defined everywhere, are continuous. Of course, step functions are useful, and you could have a function which goes very quickly from 0 to 1, but not jumping. And here comes this concept of being viscous. So these processes are such that at any finite time, it's impossible to pick out one number, because you always have processes that are oscillating around. Okay, 1/2 in this example, never mind everywhere. And so it's a bit like a pot of honey. You cannot take out one honey molecule. It's sticky or viscous. So also the intermediate value is not, does not hold in intuitionistic mathematics. Let me go a bit fast, leave time for questions. So arithmetics, obviously you can add numbers, any computable function like a sinus you can apply. You can also define, of course, this order or partial order actually. It's only a partial order indeed. And you can also introduce more concepts like when two numbers or two choice sequences are really apart, it means that you can really put your finger in between, a concept that doesn't exist in classical mathematics. Okay, so here, again, I said it already, this mathematical language is going to change what is easy to express and what is impossible even to express. So here I have a little table where I say here is what I would like from an indeterministic physics, and here what intuitionistic mathematics brings me. So in indeterministic physics, the past, present, and future are not all given at once. The future is still open. And here, digits of real numbers are not all given at once. Time passes. Numbers are processes. I find that very fascinating that in mathematics, at least in this sort of mathematics, even numbers, which is very basic, can evolve in time. Of course, not the integers, not the rationals, and so on, not even the computable numbers, but the typical numbers. Indeterminism. Numbers contain finite information. The present is thick, the continuous is viscous. You cannot just pick out a present with zero thickness. The future is open, no law of the excluded middle, becoming, choice sequences, experiencing, intuitionism. Okay, so now we have indeterministic classical mechanics as an alternative to standard quantum mechanics, same predictions. And now what can you do? Well, you can search for supplementary variables. They're well-known hidden variables, but now it's hidden variables in classical mechanics, such that the randomness becomes purely epistemic. Or the alternative would be to accept rest potentia in addition to the rest extensia, to the basic ontology. So let's start with supplementary variables. So as I already said, instead of God playing dice when potentialities become actual, God played all the dice at the initial condition and coded all the results in the initial condition. Okay, that's the same more or less. So postulating that the initial condition of all classical dynamical systems are faithfully described by mathematical real numbers is an elegant way of adding all future results while making sure that they remain inaccessible for long enough a time. You could say everything is already there because this is a real number, but you don't have to. So somehow the real numbers, the standard classical real numbers, are the hidden variables which are truly inaccessible of classical mechanics. So this is maybe one of the first way in which I successfully, hopefully, bring classical closer to quantum. So the idea of hidden variable is now part of classical indeterministic physics. And indeed, a natural wish would be to add hidden variables. Actually, these hidden variables were very, very well known. They are called real numbers. So these are already read. So if we care about how we experience reality, the later option, namely this indeterministic, intuitionistic mathematics, is superior. And there's a fact, an interesting fact, that almost all physicists accept real numbers without even noticing that these are hidden variables, while the same physicists simultaneously reject Bohmian positions as unnecessary. I think either we accept both, real numbers and Bohmian particles, or we reject both. It's kind of inconsistent to accept one without accepting the other because it's essentially the same kind of steps. Okay, now the second possibility, once you have this indeterministic physics, is to add rest potentia. And here I want to say how to go from indeterminacy, which I introduced, to indeterminism. So indeed, if you would have indeterminism with just a causal chain that starts from nowhere, that would be kind of magical. Things don't start, there is no spontaneous generation or things like that. But on the other side, claiming that a physical system has a state that is not yet fully determined is physical. Our world is full of indeterminacy. And as time passes, new information reduces that indeterminacy. Hence, this leads to indeterminism. I will illustrate it more, but you have some indeterminism, and when the position, for instance, of some particle gets better determined, it may then at the end drive it to the left or to the right. So this kind of indeterminism does not come out of the blue, is not acausal, simply some potentialities get excluded. So you have probabilities here, but not acausal. So let me continue to try to bring quantum, classical closer to quantum. So we have seen that both can be seen as indeterministic. They don't have to, but they can. And now if you consider them as indeterministic, you realize that the measurement problem is not specific quantum. Because now you can say, okay, in this indeterministic classical mechanics, I also have a measurement problem. So Lev will be especially unhappy because instead of solving the measurement problem, I introduce it into classical mechanics. But I think this is still interesting because we have the strong feeling that we understand classical mechanics very well. So if we have also this problem there, maybe it will be easier to address. And so how does it go? So this indeterminacy that we now have in standard quantum and in classical, this can be reduced in different ways. We already heard that this morning in the first talk. It could be spontaneous, GRW-like. It could be triggered by higher order demands. Actually, this we didn't hear this morning from Copenhagen, which is still, 6% for many worlds, probably 90% for Copenhagen. So we should also take it seriously. So this is really a kind of higher order demands, this macroscopic. I know it's vague, but it functions. And then you have the hidden variables. So if a real number for the classical mechanics, Bohm position, or possibly something else on the quantum side. Of course, there is the many worlds. I'm not going to forget that one. But these many worlds, I now claim it can be applied both to classical and to quantum physics. First, you may say in the quantum, you have also the Schrödinger equation, which is linear. Yes, but now here we would have the Fokker-Planck equation for the probabilities in classical mechanics, which is also linear. So I'm trying to argue, make sure to annoy Lev, that we can also have many worlds in classical mechanics. Again, I'm not at all a many world guy, so I don't want to introduce many worlds in classical mechanics, but I think it's interesting to show how much there is already in classical mechanics. Again, because we have the strong feeling that we understand classical mechanics so well, and that the problem is only on the quantum side. And so my claim is that it's not only on the quantum side. Okay, so this is what I just said now. I claim also that actually in this indeterministic classical mechanics, you also have some forms of non-locality. Because measuring here can reduce indeterminacy there. And here's a first example. Let's say you have a particle which has some indeterminacy, which is represented by this cloud. So here you have a fork, like a path, and it can go to the left or to the right. Very proud of my PowerPoint abilities. And once it is like that, you get some more determinacy that nature produces, this new information that comes. And then, for instance, the particle localizes on the left. So this is an elementary form of non-locality. Now let's take two particles. Each particle is blue thing here, have some indeterminacy on Alice and Bob's side, but you see that the relation is much better determined than the indeterminacy of Alice's particle or Bob's particle. So the green thing here is the indeterminacy of the relation between them. Now if somehow this indeterminacy of Alice's particle gets reduced, because of the strong correlation that they have, this one gets also reduced. There is no signaling here. There's no information going from one side to the other, but simply by acting on one side, you reduce the indeterminacy on the other side. I think you can imagine that in a totally classical world. And now if we continue, because here we have still some indeterminacy, we could go down smaller, but then determining this particle's position or characteristic will not fully determine that one because it cannot get below the relative indeterminacy, this green thing that we had. Okay, so what is there that is really quantum, which is not classical? And so far, the only thing that I found, is that only quantum has incompatible physical quantities. And it's only there that actually this famous Planck constant appears, in the commutation relation of position momentum or the uncertainty, Heisenberg uncertainty relation. And consequently, it is only quantum that can violate a Bell inequality. So the real strong form of quantum non-locality is really purely quantum. Okay, so this is my conclusion, and the many worlds interpretation could equally be applied to indeterministic classical mechanics. Thank you. And I will repeat it depending on what is the question.
Thank you for that. All the problems you raise with real numbers in physics seem to depend upon a view about how math represents the world that I think it's not necessary to accept, and it's one, in fact, that I personally don't find very appealing. Math doesn't interpret itself. You have to make choices about how it is you're going to use any bit of mathematics to try to latch on to the world. Just because I use a real number to represent the velocity of a particle, in Newtonian mechanics, doesn't mean that I am automatically necessarily committed to saying there is an infinite amount of information about the velocity of the particle really there in the world. Yeah. Real numbers are we can think of them as just incredibly useful tools. Almost all the mathematical information in them is just superfluous. If you like, it's descriptive fluff.
I think I agree with all what you said. It means that with classical mathematics, you can also describe classical mechanics as indeterministic. But still, I mean, most of the people talk about deterministic chaos. And deterministic chaos doesn't come out of any fact, any physical fact. It comes out from the fact that actually the equation is deterministic, and if you have everything already in the initial condition, then indeed it becomes deterministic. But if you say that the mathematics should not be interpreted in such a way that the real numbers contain all the information, then it is indeterministic.
And I also just want to very quickly register my protest. I like non-constructive proofs of existence. But the singularity theorems in GR, they're beautiful, powerful, we love them.
Absolutely excellent.
I don't want to lose
they are beautiful, but not physical.
Thank you, Nicolas, for the talk. Yeah. Should we then think that stuff that are, for example, events that is at the moment outside our light cone, that are space-like separated, I mean, are also non-physical because I have no access to them?
Yeah, I guess I wouldn't say non-physical, but they're not determined. Everything which is outside our light cone is not determined.
But isn't that putting so much emphasis on us? Like, why can't we just accept the position in which there is right now events happening?
This is
like
the last paper here.
But
the relativity of indeterminacy.
Okay, and what's the idea? Why don't you think?
The idea is a 45 minutes talk at least. And I would also add that I'm not fully sure that I understand it fully.
Because it seems to say that whatever I don't see right now or have access to just don't exist, which...
No, it's not a matter of having seen it, but if you have in principle no access, then for us this is indeterminate.
Even if you have a theory of physics that explains that light travels at a finite speed, and that this is why you at the moment have no access to it. Like when I speak about space like this. Yeah. Okay. Thank you.
Avshalom, what are you going to say?
What's the implication for irreversibility? You have a system.
Oh, it's completely reversible. Time really passes.
Okay, so if you want to time reverse something to see whether entropy decreases, if everything is deterministic, you will have it. If there is one indeterministic event and you want to time reverse it, entropy will rise again, right?
Yeah, so indeed, I mean, but even there are now papers out where they show that chaos is so important that even a fluctuation on the Planck scale at the Big Bang
I'm talking classics.
would change the shape of the cosmos.
So that means that in future technology, which is not very far, you will see that reversibility fails very often. Even
Yeah. But I think it's quite obvious. I mean, there are many experiments that show that in practice, irreversibility is a fact.
No, but
just put all the air molecules of this room in a corner, open that box, and that is an irreversible process.
Would unitarity be conserved? Let me rephrase it.
Unitarity. Yes, I don't believe in unitarity.
Oh, good. Thank you.
Are you still going to talk to me?
Oh, sure. I love you. I love you even more. Thank you.
Okay, thank you.